Kia ora Year 12, here's part 2 of what you've missed in class yesterday and today. So this is going to be mainly all about the factor theorem, but we're going to start with a bit of revision of long division and the remainder theorem. So if you haven't watched part 1, you might want to spend some time doing that. It's 14 minutes long, just skip through if it goes too slowly. It's all based on Delta chapter 26. Okay, so this was the start. I determined the values of P and Q. If this is true, we've got to do this one by long division, or we can do it actually by inspection if we're pretty confident. I'll go through both of those, but long division first. Just change the pen colour. So we start as usual and we say we want to divide x cubed plus 27. So we put in our missing powers of x, right, going in descending order. So x plus 3 into that. So I think I haven't left enough room here, but never mind. So x squared times x will match up to the x cubed. Subtract that off and we get negative 3x squared plus 0x. What times x will give me that negative 3x squared minus 3x. Right, so we get minus 3x squared minus 9x. Right, subtracting here, we get 9. I'm going to get into trouble with my app on the iPad. There we are, 9x plus 27. So that's going to be a plus 9. Right, now I haven't got room to do that last line, but you should keep going with it and you'll see that that comes out exactly. So what that's telling me is that I can write x cubed plus 27 as x plus 3 times x squared minus 3x plus 9. So in here we've got p equals negative 3 and q equals 9. Now I could have done that by just looking because I need to squish things in a bit here, hang on. I know that that's a plus 27, I've got a plus 3 here, so I know that q's got to be 9. Right, so let's look at this down here. We can write it as x plus 3 times x squared plus something plus 9. Now, what have we got happening with the x squareds? Well, we want to end up with no x squareds, right? But we know we've got plus 3x squareds from this little term. So that means that we have to have the px times the x getting rid of those. So that has to be minus, oh, cool, minus 3x. So in this case, it would have been faster to do it this way, right? But I want you having the skills to do both. Right, so for this one we had to do some factorising, but for this next question we don't have to do any factorising, we just have to use the remainder theorem. Okay, so determine the remainder when this polynomial is divided by the following 3 factors. So I'm going to insert a new slide to do this, but in all of these cases all we have to do is evaluate the value of the polynomial at a particular value. Okay, so the polynomial we're evaluating, we're going to write as p of x. So always start these problems off like this, because we need to see what you're thinking. So that's my polynomial, it's got degree 3, and we're asked to figure out the remainder when we divide by x plus 2. Okay, so what we do to use the remainder theorem is we say, well, when would x plus 2 equal 0? X is negative 2. So this is the value that we're going to sub in here. So we have p at negative 2, so that equals negative 8 plus 6 plus 6, right, here, plus 1, so that equals 7. We do the same thing for part B, which was to evaluate this. What is the remainder when it's divided by x minus 3? So I evaluate the polynomial at 3 and I get 27 plus 18 minus 9 plus 1, right? So I'm substituting in there, which is 37. Now the last one, just be a wee bit careful with that. We've got this as my divisor. So what will happen when I divide this polynomial by 2x minus 3? So I set 2x minus 3 equals 0. to say x equals 1.5. And then we evaluate at 1.5. Now I did that in class, but I can't remember what we got. And my calculator's not here, so it's whatever that is. Okay, you guys can figure that out. Right, on to the next slide. So this is where the new stuff comes in. Okay, so we have this really, really cool bit of maths called the factor theorem. Okay, and the factor theorem is going to let us factorise polynomials that look really difficult to factorise. Now, I didn't do the proof of this, but I want you to be able to use it. And what it is it says that if we can evaluate the polynomial at a value a, and it turns out to be 0, then we have found a factor of that polynomial. And the factor will be x minus a. So that's the theorem working in one direction, right? So if p of a equals 0, then x minus a is a factor. And that's going to be the direction we use for most of this week. But it works the other way as well. If I know that x minus a is a factor, well then I know that the remainder is 0, and then p of a will equal 0. Okay, so I popped this little bit in from delta. Now I'm usually pretty uptight about not including bits from delta in any videos. This is not very good, but I figure just this one won't hurt. Okay, so this is out of the book we've got in the classroom, and there's a similar little section in Delta chapter 26. So now we're going to look at how we can use this to do to solve problems. Right, so the next two slides are in here. So pause the video if you want to have a look at this. This is the proof going in one direction, and this is the proof going in the other direction. Now, next thing we're going to look at how to use it. Okay, so the first one, write working and some calculations to show that x plus 1 is a factor of this polynomial. So we start by writing p of x is equal to x to the power of 4 minus x cubed plus x squared minus 2x minus 5. So we're working with x plus 1, so that means we want to evaluate at x equals negative 1. So all I have to do is to substitute in here, so negative 1 to the power of 4, 1, minus negative 1, plus 1, plus 2, minus 5. Alright, so we've got 1 plus 1 is 2, 3, 5, 0. So by the factor theorem, which I'll write as FT, not Financial Times, factor theorem, by the factor theorem, x plus 1 equals 0 is a factor. Okay, done. Easy. Right, explain whether or not x plus 2 is a factor of this expression. So we're going to substitute in p at negative 2, and we get whatever we get. Right, you can figure that out. You don't need me to do that. And that is not equal to 0. Therefore, x plus 2 is not a factor. Right, now the next two I'm going to do on a new slide because I want to talk about a couple of ways we can do them. And the first one is to determine the factors of this cubic equation. Right, so until today you looked at cubics, and unless they were really easy ones we couldn't factorise them, but that has now changed. Okay, so we're going to factorise both of these two things here. Right, so we write our polynomial p of x is equal to x cubed minus 5x squared plus 2x plus 8. And we're trying to look for real numbers that will be factors. Now, what goes into 8? Well, my options are plus or minus 1, 2, 4, and 8. So always start at the bottom end. Let's evaluate that polynomial at x equals 1. We get 1 minus 5 plus 2 plus 8. Definitely not going to work. Not equal to 0. So x minus 1 is not a factor. But let's try negative 1. So we're going to have negative 1 minus 5 minus 2 plus 8. That is equal to 0. So x plus 1 is a factor. Happy face. There we go. So we're asked to find all of the factors. Now there are a couple of ways to go here. I'll show you in class how to do this on your calculator, but if you can play with it now. If you use the table function on your graphics calculator, you can put the equation in, and then you can put in a bunch of possible values. Okay, and you'll get, probably, if you're lucky, you'll get a couple of the factors popping out here with zeros on this side. And so that will give you more than one factor. But the other low-tech way to go, with more brain, is to say, well, we found our first factor, so it shouldn't be too bad to do the rest. So let's see how that works. So we know that p of x has got x plus 1 as a factor. So I could go away and do my long division, right? And you should do that just to get good at it. Or I could just write it out like this. So I've got my x plus 1. I know that I've got to have x squared to get the x cubed term. And I know that this thing here is going to be a quadratic, and this must be plus 8. So now I do this matching up idea that I had before. I've got to get a negative 5x squared coming out here. Right? I've got plus 1x squared here, so whatever comes in here has got to be giving me a minus 6x squared. Okay? Or we could have done it by looking at the plus 2. Okay, so I'm going to erase it and show you the other way to think about it with the plus 2x. Right, so I've got this x cubed and I've got the plus 8. Whatever number I put in here has got to end up, when I expand, giving me plus 2x. Well, I've got plus 8x here. So to end up with plus 2x, I must have minus 6x. So it doesn't matter which way we do that. Now, I quite like that method. It depends if you're a long division person or expanding out the short way. So we're not finished yet, because now we need to work out how we can factorize this. Now, in this case, it factorizes and has two integer factors. So we have integer roots, sorry, not integer factors. So x plus 1 times x minus 4, x minus 2. Alright, so that's how to use the factor theorem to factorise a higher order polynomial. We've got one more to do, but I think this video is probably long enough, so you can play with the other one yourself. Exercise 26.3 has got lots of really good examples of problems where there are cubics and you're asked to factorise fully. Okay, so that should be tons to keep you going. If you've had time to watch this, well done, and good luck for the rest of your exams.